Hello students, how are you? Welcome to my channel. Today we are going to just discuss about quantum mechanics. Today it is the first lecture on the quantum mechanics. Quantum mechanics is defined as the branch of physics which deals with the study of motion of the subatomic particles like electron, proton, neutron and etc. So in today's lecture, my topic would be about de-Broglie hypothesis. De-Broglie hypothesis. That is the concept of matter waves. Okay, what is this concept? Actually, we know that our universe consists of matter and radiation. Well, radiation has dual nature, particle as well as wave. There are certain properties of the radiation which can be explained by assuming that radiation has particle nature. These properties include black body radiation, photoelectric effect, which is famous and almost every student has knowledge about it, and Compton effect, and many others, of course. But these three are the major properties of radiation which we can explain by assuming particle nature of light only. Similarly, there are the properties of the radiation which we can explain only by using the wave nature. These are interference, polarization, diffraction. So that the radiation has dual nature and our universe contains only radiation and matter. And it gave idea to de-Broglie that if radiation can possess dual nature, then the matter can also possess dual nature. So we already knew about prototype nature of matter, that is the particle nature. Here what is important for us to know that what is the difference between particle and wave nature? It is actually the exchange of the transfer of the momentum. Particle nature is distinctive from the wave nature for the transfer of momentum. When two particles strike with each other, they cannot cross with each other. They actually transfer momentum from one particle to another particle. On the other hand, waves can pass through each other. So therefore, the transfer of momentum is not the basic property of the waves. So matter, if it possesses particle nature, which is prototype nature of the matter, then the new nature about which de-Broglie talked or said was the wave nature of the matter. And this concept that matter possesses dual nature just like radiation is called de-Broglie's hypothesis. And this was later on proved experimentally by famous Davison and Germer experiment that matter can show diffraction. There, these two experimentalists were able to show that the electron beam from bismuth was able to give diffraction pattern. Since diffraction is the property of the waves only, therefore that experiment was experimental proof of the wave nature of the matter. So the wave which is attached with an object or matter has many names. The first name is of course de-Broglie wave. second name to the wave attached with the matter is called, this is matter wave. It is also called pilot wave, and it is also called as guide wave. These are the four famous names for the wave attached with a particle. So we are now going to find the expression for the wavelength of the wave attached with a particle. Of course, we know that the expression we have studied in the lower classes is given by lambda is equal to h upon mv, where h is Planck's constant, m is the mass of object in motion, and v is its speed, and lambda is the wavelength of the wave attached with the particle, of course. We are going to prove this result by using the results of Einstein's special theory of relativity. So since we are going to use Einstein's theory of relativity here in this article, we must know some basic expressions that we will be following in the article to prove this expression. So the first thing that we must know is that the mass of an object in motion, let us say that is m, is related to the mass of the object at rest, that is m0, by this relation, m is equal to m0, 1 minus v square upon c square, where m is mass in motion, m0 is rest mass, v is speed of object, and c is speed of light in vacuum. Similarly, from Einstein's theory, we must know that the total energy contained in a body of object or body of mass m is given by E is equal to mc square. This is the first equation that we must remember. This is the second equation that we must remember. And the third equation that we must remember for proving lambda is equal to h upon mb is that if we want to find the relation between the times of two inertial frames of reference, let us say this frame of reference is S, this frame of reference is S dash. Suppose S dash is traveling along x-axis with velocity v, and the time of this clock is represented by symbol t, and time of this clock is represented by symbol t dash. Then t dash is related to t by the following relation: t dash is equal to t minus v upon c square x upon square root of 1 minus v square by c square. So this is the relation we must remember, and it transforms time of frame S dash into, it relates actually time of frame S dash with the time of frame S at a point whose position with respect to S is x. This is the third relation that we should remember. Fourth relation that we must remember is that the equation of a progressive wave traveling along plus x-axis is given by y is equal to a sine omega t minus kx, where a is the amplitude of the progressive wave, omega is its angular frequency, and k is called propagation constant. Of course, omega is equal to 2 pi nu, where nu is the frequency, and k is equal to 2 pi by lambda, where lambda is the wavelength, and psi is called wave function. Similarly, the equation of a stationary wave, let I write here P, P stands for progressive, and let I write here as S, S stands for stationary wave. It is given by A sine omega t and cos kx. Please remember these 5 equations: first, second, third, fourth, and fifth. These 5 equations will be required to prove lambda is equal to h upon mb. One thing that we must remember, that in equation 4, instead of sine, we can have cos also, and we can have plus here also. That depends upon the direction in which the wave is traveling. If it is traveling along plus x-axis, then here it should be minus. And if it is traveling along minus x-axis, then here it should be plus. Instead of sine, if someone wants to put cos, he or she may do that. But that sine and cos differ only by a phase difference of 90 or pi by 2 radian. We know about this. In case of stationary wave, there will be two trigonometric functions. One of them will be sine, other will be cos, and vice versa. And the argument of one trigonometric function will be a function of time, and argument of second trigonometric function will be a function of position, that is x. So that is the basic difference between the standard equation of a progressive wave and a stationary wave. Let us now try to prove this expression lambda is equal to h upon mv. For that, we have to just formulate the problem, and for doing that, suppose there are two frames of reference, S and S dash, and we show them in such a way that their x-axis coincide with each other, like this one. So this is the y-axis, this is the x-axis, this is the z-axis. Z, y, and x. This is the origin. I would just show a clock in the frame S, whose time is represented by symbol T. This frame is designated as S. Let us say there is another frame of reference whose y-axis is represented by y dash. This frame is called S dash. The time in this frame is represented by symbol T dash. Origin of this frame is O dash. This is the z-axis represented by z dash. Origin is O dash. And x-axis of this frame of reference is x dash. Now look, their x-axis of both frames are coinciding with each other, and their y-axis are parallel each other, and z-axis are also parallel to each other. We assume that there is an object attached to the x-axis of frame S dash. On the other hand, S dash is traveling along x-axis with a uniform velocity v. So this object is attached to the x-axis of frame S dash. It means this object, when seen in frame S dash, will appear to be in rest. And the same object, when seen from S, will appear to be in motion. And when seen from S, its velocity in S will be same as velocity of frame S dash. So I can say that v is velocity of S dash, as well as it is the velocity of this object in the frame S. Since it is in motion in the frame S, therefore its mass in S cannot be same as the mass in S dash. In S dash, the object is assumed to be at rest. Let us say the mass of the object in S dash is m0. Same object will show a heavy mass, and let us say its mass in motion in S frame is m. And the position of this object from O dash is x dash, and position of same object from O is x. It is important to note here that x dash is constant because this object is at rest with respect to O dash, so x dash will always remain same. On the other hand, x will continue to increase since the object is going away from origin with the time. So the starting point, I have now described this diagram. Now let us write the relation between m and m0. According to Einstein, m is equal to m0 divided by square root of 1 minus v square y c square. This is the first relation that we must know. Now, since we have assumed that this object possesses wave nature, and if wave is attached with the object, this wave must be observable in frame S as well as in frame S dash. Since in the frame S dash the object is at rest, the wave attached with it must be stationary wave. And similarly, if the object appears to be in motion in the frame S, the wave attached with it, same wave attached with it, when seen from S, must appear to be a progressive wave. And what is the difference between the forms of psi S and psi P? I have already written. You might have noted it down. Okay, for the starting point, let us assume that the wave function attached with the object in the frame S dash is given by psi S equal to A dash sine of omega dash t dash minus k dash x dash. I have put dash over all the constants and variables in this equation to just indicate that this equation is written in the frame S dash. I think I have written wrong equation. Let me correct it. Actually, since the wave is stationary, the equation must be A dash sine omega dash t dash and cos of k dash and x dash. Let us say this is equation number 2. Now it is correct as per the formulation described earlier. Since x dash is constant, k dash is constant, a dash is also constant, I can write this equation like a sine omega dash and t dash. Let us say this is equation number 3, where what I have written a, which is a new constant, as product of two different constants, a dash cos of k dash x dash, because x dash is a constant quantity. Now let us move further, and we know this equation that t dash is equal to t minus v by c square x upon square root of 1 minus v square by c square. If I put this value of t dash in equation 3, then our wave function will transform from S dash frame to S frame. So I would leave this subscript S, because now the wave has been transformed. The wave function has been transformed from S dash to S. Therefore, new wave function in S will appear to be psi, and it is now given by A sine, I would put a square bracket here, omega dash. Instead of t dash, I would rather put t minus v upon c square x upon square root of 1 minus v square by c square, and in the next line I can write it as a sine omega into t minus v by c square and x. Let us say this is equation number 4. Here I have written omega equal to omega dash upon square root of 1 minus v square by c square. Now this denominator is a constant quantity. Why? Because v is the velocity of the frame S dash, which is an inertial frame of reference. The velocity is a constant quantity, and c is a constant quantity according to the laws of special theory of relativity. So this denominator is a constant quantity. So I have divided omega dash by a constant factor, and I denoted it by a new factor omega, which will turn out to be the angular frequency of the de-Broglie wave in the frame S. Kindly remember, omega dash is the angular frequency of de-Broglie wave in the frame S dash. Now I can just take this omega inside, and equation 4 can be written as psi is equal to A sine omega t minus omega v by c square into x, which can be further simplified as psi is equal to A sine omega t minus kx. Equation number 5, where I have assumed that omega v upon c square is equal to k, say. So we can see that in equation 5 we have transformed. We started with the wave function of the wave in the frame S dash, and we took its form to be standard form of a stationary wave. Then we applied the transformation of special theory of relativity, and when we solved it and we just readjusted the terms, and we found that the wave function of the particle in the frame S matches with the standard progressive wave equation. I can just put subscript P here. Why? Because this wave function is different from this wave function in the manner that it represents stationary wave in S dash, and the same wave function when transformed into S represents a progressive wave in the frame S. It has to be so. Why? Because object is at rest in the frame S dash, and the same object appears to be in motion in the frame S. Therefore, the stationary wave function must transform into a progressive wave function when we do appropriate transformations. Now, let us find the speed of the wave attached with the particle. Let us say the speed of this wave, which is given in equation 5, let us say Vp is the speed of the wave. Vp is also called phase velocity. It is also called wave velocity. And it is the velocity of the de-Broglie wave attached with the particle. Now, the velocity of every wave is the product of two things, that is frequency and wavelength. I can modify this equation by multiplying and dividing by 2 pi. Now, if I write this equation further by this 2 pi nu upon 2 pi by lambda, there is nothing wrong in it, but it will give me a new expression for the phase velocity, which would be ratio of omega to k. I can write this as equation number 7. It is a very useful result. We will be using it more frequently in the articles to come. So we can also remember that the wave, any wave, this expression is actually valid for any wave, not only for matter wave. We can write phase velocity is equal to the ratio of coefficient of t to the coefficient of x, because whatever is coefficient of t in 5 is angular frequency or angular velocity, and whatever is coefficient of x in equation 5 is propagation constant. Let us now move further and we put the values of omega and k. Rather, we will be putting the value of k only. And if we put the value of k from equation number 6, which I have just erased, I know its value. So if we put this value in 7, then Vp will be equal to omega divided by omega v upon c square. This omega and this omega will cancel. It will be c square upon v. Therefore, the velocity of de-Broglie waves is equal to c square upon v. In this expression, let me write this as equation number 8. In this expression, we have all these three are the velocities. However, this is the velocity of object in the frame S. This is the velocity of light in vacuum. This is the velocity of de-Broglie wave in the frame S, of course. Now equation 8 gives some strange result to us. Why? Because if I write this equation like this, it is equal to C into C by V. Now this quantity in the round bracket is always greater than 1. Always greater than 1. Because according to laws of special theory of relativity, no object can travel faster than speed of light. So if this quantity is always greater than 1, then if I multiply C by something which is greater than 1, I can clearly understand that Vp is greater than C always. This means de-Broglie waves travel faster than the velocity of light in vacuum. This appears to be a strange result, but remember that this result does not violate relativity laws. Why? Because relativity laws, they bind any object to travel faster than speed of light, but there is no such binding on the waves. If waves travel faster than speed of light, then there is as such no violation of laws of special theory of relativity. So we must remember it that Vp is greater than C. De-Broglie waves travel faster than the speed of light. So our purpose in this article was not to find the velocity of de-Broglie waves. Of course, these are found as a usual work process, but our purpose is to find the wavelength of the de-Broglie waves. To find that formula for the wavelength of the de-Broglie waves, I assume that this is the shape of the wave attached with object. I have a solid reason for assuming this kind of shape with the object. But however, I will not discuss this in this lecture. We will discuss it in the next lecture. Of course, we are not going to skip it. So the shape of the wave function attached with the particle, I have written it like this. I have shown it like this. And object is like this. Now, this is the object and this is the wave attached with the particle. This object cannot come out of this wave region. This wave region is called wave packet. Why it is called wave packet? Because we know that light is emitted in the form of bundles of energy, and every bundle of energy is called photon. So according to de-Broglie, even matter waves are emitted in the form of bundles, and these bundles are called wave packets, or it is also called a wave group. And according to de-Broglie, the formula which the energy which is used for finding the energy of a photon is given by E is equal to h nu. It is famous formula. And according to de-Broglie, since this is a packet of energy, its energy is also found by this formula. The same formula is applicable for finding the energy of the wave packet. On the other hand, according to Einstein's special theory of relativity, since this is the object whose mass is m, so therefore its energy must be given by E is equal to mc square. Since the wave packet belongs to the particle only, therefore this energy, which is the energy of the wave packet, and this energy, which is the energy of the object, which is confined within the wave packet, must be same. It means we have two different methods of finding the energy, either through the wave packet expression or through the mass relation. Rather, we will use both of these expressions and equate them to find our result for the wavelength. In case of photons, we know that E is equal to h nu is further written by hc by lambda. Now, here for photons, we cannot use c. Why? Because frequency, speed of de-Broglie waves is not c. Rather, the speed of de-Broglie waves is Vp. So I can extend this expression E is equal to h nu for de-Broglie waves by just writing Vp in place of C here. So therefore this equation will be written as E is equal to HVP upon lambda. If I further put the value of Vp from equation number 8 here, then E can be written as H by lambda multiplied by C square upon V. Let us say this is equation number 9. And we also know that E is equal to mc square. This is equation number 10. Now, if I equate equation 9 and equation 10, I would rather immediately get my desired result. Equating equation 9 and 10, we get mc square equals to h by lambda c square upon v. C square will cancel with c square and lambda will be equal to h upon mv, which is my desired result. I can also write it as lambda is equal to h upon p, where p is the magnitude of the linear momentum of the object in the frame S on also, of course. Now I can write this equation as equation number 11. What is important point to remember here that this mass m is not the rest mass, it is the mass in motion. This is the first thing that we must remember. Second thing that we must remember is that we have obtained this result by using the laws of relativity. So therefore, equation number 11 is valid at low speeds as well as high speeds. In fact, we can say that equation 11 is a relativistic expression. We can use this expression at any speed so far. Let us now take an example what I mean by saying this important property of equation 11. Suppose we have an electron. Since it is an electron that I have talked, therefore its rest mass will be equal to 9.1 into 10 raised to power minus 31 kg. Now suppose this electron is moving with the speed v is equal to 1.5 into 10 raised to power 8 meter per second. Now this speed is comparable with the speed of light. Now if I want to find the de-Broglie wavelength of the wave attached with this electron, then I cannot use this mass. This mass cannot be used here. I have to first find mass in motion. That will be given by m is equal to m0 divided by square by c square, which will be equal to m0 divided by square root of 1 minus 3 into, it's not 3, it is 1.5 into 10 raised to power 8 upon 3 into 10 raised to power 8 whole square. Now that will become 1 by 4 and it will be m0 into square root of 3 by 4. So this will be equal to 2 upon square root of 3 m0, that will be equal to 2.1.732 m0. So if I just put this value, then it will be 2 upon 1.732 into 9.1 into 10 raised to power minus 31, which will become 18.2 upon 1.732 into 10 raised to power minus 31 kilogram. So this is the mass of electron that we must use in equation 11 to find the wavelength of the electron. Hence the final value of the wavelength of the electron traveling with such a speed will be obtained by this formula. Lambda is equal to h upon mv. It will be equal to 6.63 into 10 raised to power minus 34 joule into second divided by 18.2 divided by 18.2 upon 1.732 into 10 raised to power minus 31 multiplied by this is 1.5 into 10 raised to power 8. Now this will give you correct expression for the wavelength of the electron moving with such a speed in the units of meter. So while doing numericals, this must be taken care of, that if any object, not only the electron, if any object which is traveling with a speed that is comparable with the speed of light, you must transform the mass at rest into mass in motion first. Only then you must try to use this expression. It is a relativistic expression. So students, I would rather stop here, and in the next lecture we will discuss something more about the de-Broglie concept, and some other examples of de-Broglie concept will be discussed. I hope you have enjoyed this lecture, and I would stop here and we would continue our discussion on de-Broglie hypothesis from in the next lecture onward. Thank you.